What if the universe itself could crush matter into forms so bizarre they defy everything we know about physics? Picture this, a single teaspoon of material so dense it weighs more than 1 billion elephants. Sounds impossible, right? Yet this is the reality of the extreme pressures found in the cosmos. From the crushing cores of neutron stars to the mind-bending forces near black holes, the universe is a laboratory of unimaginable extremes. These pressures don't just bend the rules, they rewrite them, creating phenomena that challenge our understanding of reality. In this video, we're diving into 50 astonishing facts about the universe's most extreme pressures. By the end, you'll uncover how these cosmic forces shape everything from the tiniest particles to the largest structures in existence. So, are you ready to explore the universe's most extreme environments? Let's begin. Now, let's zoom in on one of the most extreme environments in the universe, the core of a neutron star. Imagine taking a sugar cube and compressing it so tightly that it weighs as much as 1 billion elephants. That's the kind of pressure we're talking about here. At the heart of a neutron star, matter is squeezed to densities so extreme that atoms can't even exist in their normal form. Instead, protons and electrons are forced together, merging into neutrons. This creates a bizarre, ultra-dense material known as neutronium, where a single teaspoon would weigh billions of tons. But it doesn't stop there. The pressure is so intense that it pushes matter into even stranger states, like quark-gluon plasma, where the building blocks of protons and neutrons break down into their most fundamental components. These conditions are so extreme that they challenge our understanding of physics, offering a glimpse into how matter behaves under pressures that simply don't exist anywhere else in the universe. And as we'll see, this is just the beginning of the cosmic extremes waiting to be uncovered. Now, let's step away from the core and take a closer look at the surface of a neutron star. While the core is a mind-bending realm of neutronium and quark-gluon plasma, the surface is no less extreme. Here, the gravitational pull is so overwhelming that it flattens atoms into an incredibly thin crust, almost like a cosmic pancake. Imagine the weight of millions of Earth atmospheres pressing down on every square inch. That's the kind of pressure we're dealing with on the surface of a neutron star. This immense force crushes atoms so tightly that electrons are forced into the nucleus, merging with protons to form even more neutrons. The result is a solid crust made of ultra-dense matter, but even this crust is far from ordinary. It's so dense that a single teaspoon of it would weigh as much as a mountain. And yet, despite this crushing pressure, the surface of a neutron star is also a place of incredible activity. Magnetic fields trillions of times stronger than Earth ripple through this thin layer, creating starquakes and bursts of energy that can be detected across the galaxy. What's truly fascinating is how this surface pressure contrasts with the vacuum of space just above it. While the neutron star's gravity creates a crushing environment, the space around it is nearly empty, making the transition from extreme pressure to near nothingness one of the most dramatic boundaries in the universe. This interplay between unimaginable pressure and the void of space is a reminder of just how extreme and diverse the cosmos can be. And as we'll see next, the story of pressure in the universe only gets more astonishing from here. Now, let's venture into one of the most mysterious and extreme environments in the universe, the event horizon of a black hole. This is the point of no return, where the gravitational pull becomes so overwhelming that not even light can escape. The pressure near the event horizon is unimaginable, creating a zone where the laws of physics as we know them begin to break down. As matter approaches the event horizon, it experiences something called tidal forces. These forces are so intense that they stretch and compress anything that gets too close. Imagine being pulled in two directions at once, stretched like a piece of spaghetti while simultaneously being crushed from the sides. This is what happens to stars, gas, or even spacecraft that venture too close to a black hole. The side of the object facing the black hole feels a much stronger gravitational pull than the side facing away, leading to this dramatic stretching and compressing effect known as spaghettification. But the pressure doesn't stop there. As matter spirals closer to the event horizon, it heats up to incredible temperatures, emitting intense radiation. This process creates a glowing ring of superheated gas and dust known as an accretion disk, which orbits the black hole at nearly the speed of light. The friction and pressure within this disk are so extreme that they can outshine entire galaxies. What makes the event horizon even more fascinating is its role as a cosmic boundary. Once something crosses it, there's no turning back. The pressure and gravity are so overpowering that they warp space and time itself, creating a one-way journey into the unknown. This is a place where the universe's most extreme pressures reveal the true power of gravity, bending reality in ways that challenge our understanding of physics. And as we'll see next, the story of pressure in the cosmos only grows more astonishing as we explore the explosive forces of supernova. Now, let's shift our focus to one of the most spectacular and violent events in the universe, supernova explosions. These cosmic detonations are so powerful that, for a brief moment, they can outshine entire galaxies. But what makes them truly remarkable is the extreme pressure they generate, which plays a crucial role in shaping the cosmos as we know it. At the heart of a supernova lies a dying star, one that has exhausted its nuclear fuel. When this happens, the star's core collapses under its own gravity, creating pressures so immense that they trigger a catastrophic explosion. The force of this explosion is staggering, releasing more energy in a few seconds than our Sun will emit over its entire lifetime. This incredible pressure doesn't just destroy, it creates. During the explosion, temperatures and pressures reach such extremes that they forge heavy elements like gold, uranium, and platinum. These elements, which are essential for life and technology, are scattered across the universe by the supernova's shockwaves. In a very real sense, the jewelry you wear or the electronics you use owe their existence to the extreme pressures of these stellar explosions. But the story doesn't end there. The shockwaves from supernova also compress nearby gas and dust, triggering the formation of new stars and planets. This cycle of destruction and creation is a testament to the universe's ability to transform chaos into beauty. As we'll see next, the pressures inside white dwarfs reveal another fascinating chapter in the story of cosmic extremes. Now, let's turn our attention to the quiet yet extraordinary remnants of stars, white dwarfs. These dense stellar cores are the final stages of life for stars like our Sun, and they hold secrets of some of the most extreme pressures in the universe. Inside a white dwarf, the pressure is so intense that it defies our everyday understanding of matter. When a star exhausts its nuclear fuel, it sheds its outer layers, leaving behind a hot, dense core. This core is supported not by nuclear reactions, but by something called electron degeneracy pressure. This is a quantum mechanical effect where electrons are packed so tightly that they resist further compression, creating a force strong enough to counteract the pull of gravity. To put this into perspective, the pressure at the center of a white dwarf is millions of times greater than the pressure at the center of Earth. Imagine squeezing the mass of the Sun into an object the size of Earth. That's the density we're talking about. Yet, despite this crushing pressure, white dwarfs remain stable, glowing faintly as they slowly cool over billions of years. What's truly fascinating is how this pressure shapes the fate of these stellar remnants. Without electron degeneracy pressure, white dwarfs would collapse further, potentially forming neutron stars or even black holes. Instead, they stand as cosmic monuments to the delicate balance between gravity and quantum forces. As we'll explore next, the Sun's core reveals another layer of extreme pressure, where nuclear fusion powers the very heart of our solar system. Now, shifting our gaze to the heart of our solar system, we arrive at the Sun's core, a place where unimaginable pressures and temperatures work in harmony to power the very engine of life. At the center of the Sun, the pressure is so extreme that it crushes hydrogen atoms together, igniting the process of nuclear fusion. This is where the Sun's incredible energy is born, and it's all thanks to the delicate balance of gravity and pressure. The pressure at the Sun's core is estimated to be around 250 billion times greater than the atmospheric pressure we experience on Earth. To put that into perspective, it's like stacking 300,000 Earths on top of each other, all pressing down on a single point. This immense pressure forces hydrogen nuclei to collide at incredible speeds, fusing them into helium and releasing vast amounts of energy in the process. This energy, generated deep within the Sun's core, takes thousands of years to travel outward, eventually reaching the surface and radiating into space as sunlight. It's this same energy that has sustained life on Earth for billions of years, making the Sun's core not just a marvel of physics, but a cornerstone of our existence. What's truly remarkable is how this pressure has remained constant over billions of years, allowing the Sun to shine steadily and reliably. Without this delicate balance, the Sun would either collapse under its own gravity or explode in a catastrophic release of energy. Instead, it continues to burn, a testament to the incredible forces at work in the universe. As we move forward, we'll explore the crushing pressures inside gas giants like Jupiter, where hydrogen is transformed into a metallic state under conditions that defy imagination. Now let's journey beyond the Sun and into the realm of gas giants, where the pressures are so intense they transform ordinary elements into extraordinary states. Take Jupiter, for example, the largest planet in our solar system. Beneath its swirling clouds of hydrogen and helium lies a world of unimaginable forces. Deep within Jupiter's interior, the pressure becomes so extreme that hydrogen, the lightest and most abundant element in the universe, is compressed into a metallic state. This metallic hydrogen is unlike anything we encounter on Earth. It's a superconductor capable of conducting electricity with zero resistance, and it's this transformation that gives Jupiter its incredibly powerful magnetic field. The pressure required to create metallic hydrogen is staggering millions of times greater than Earth's atmospheric pressure. To visualize this, imagine the weight of thousands of Earths pressing down on a single point. This immense force squeezes hydrogen atoms so tightly that their electrons break free, forming a sea of charged particles. It's this sea of electrons that allows metallic hydrogen to conduct electricity and generate Jupiter's magnetic field, which is over 20,000 times stronger than Earth. Jupiter's magnetic field isn't just strong, it's vast, stretching millions of kilometers into space. This magnetic shield traps charged particles, creating intense radiation belts that would be deadly to any spacecraft venturing too close. It's a reminder of the incredible forces at play within gas giants, where pressure doesn't just shape matter. It creates phenomena that dominate entire planetary systems. What's fascinating is that this metallic hydrogen layer isn't static. It's in constant motion, churning and flowing like a liquid metal ocean. This movement, combined with Jupiter's rapid rotation, generates electric currents that power its magnetic field. It's a dynamic process, one that highlights the intricate relationship between pressure, matter, and energy in the universe. As we continue our exploration, we'll delve into the pressures of the Big Bang, where the entire universe was compressed into an infinitely dense point, setting the stage for everything we see today. Now let's take a step back in time, way back to the very beginning of everything. The Big Bang wasn't just an explosion. It was the birth of the universe itself, and the pressures involved were beyond anything we can fully comprehend. Picture this: the entire cosmos, all the matter and energy that exists today, compressed into a single, infinitely dense point. This point, known as a singularity, was so unimaginably small and dense that the laws of physics as we know them break down when we try to describe it. The pressure at this moment was so extreme that it defies comparison. To put it into perspective, the pressure inside a neutron star, which we've already discussed, is immense, but the pressure during the Big Bang was on an entirely different scale. It was a pressure so intense that it didn't just compress matter, it created the very fabric of space and time. This unimaginable force didn't just sit still, it unleashed an explosive expansion, sending the universe hurtling outward at an incredible rate. This rapid expansion, known as cosmic inflation, happened in a fraction of a second. The pressure from the Big Bang didn't just push matter apart, it stretched space itself, creating the vast, expanding universe we see today. It's this initial burst of pressure and energy that set the stage for everything: galaxies, stars, planets, and even us. What's truly mind-blowing is that the remnants of this pressure are still detectable today. The cosmic microwave background radiation, often called the afterglow of the Big Bang, is a faint echo of that unimaginable pressure and heat. It's like a snapshot of the universe when it was just a few 100,000 years old, and it gives us a glimpse into the extreme conditions that shaped everything we know. As we move forward, we'll explore how these pressures didn't just create the universe, they continue to shape it, driving phenomena like dark energy and cosmic expansion. But for now, let's marvel at the sheer scale of the Big Bang, a moment when pressure wasn't just a force, it was the force that birthed the cosmos. Now, let's zoom in on something truly extraordinary, a state of matter so extreme that it only existed for a fleeting moment after the Big Bang. This is quark-gluon plasma, a soup of fundamental particles that scientists have recreated in some of the most advanced laboratories on Earth. To understand this, we need to go back to the earliest moments of the universe, when temperatures and pressures were so high that even protons and neutrons couldn't hold their shape. Instead, they broke down into their most basic building blocks, quarks and gluons. Quarks are the tiny particles that make up protons and neutrons, while gluons are the glue that holds them together. But under the extreme pressures and temperatures of the early universe, quarks and gluons weren't bound together, they floated freely in a chaotic, superheated soup. This is quark-gluon plasma, a state of matter that hasn't existed naturally since the universe was just a fraction of a second old. Today, scientists recreate these conditions using massive particle accelerators like the Large Hadron Collider. By smashing heavy ions together at nearly the speed of light, they generate temperatures over 100,000 times hotter than the core of the Sun, and pressures so intense that they momentarily recreate the quark-gluon plasma. These experiments give us a glimpse into the universe's earliest moments, helping us understand how matter evolved from this primordial soup into the protons, neutrons, and atoms that make up everything we see today. What's fascinating is that quark-gluon plasma behaves more like a liquid than a gas, flowing with almost no resistance. This discovery has reshaped our understanding of the early universe, revealing that it was far more dynamic and fluid than we once thought. By studying this exotic state of matter, scientists are piecing together the story of how the universe transitioned from a sea of free quarks and gluons to the structured cosmos we know today. As we continue our journey through the universe's most extreme pressures, let's keep in mind that these experiments aren't just about recreating the past, they're about unlocking the secrets of matter itself. Next, we'll explore how these extreme pressures manifest in the magnetic monsters known as magnetars, where the forces at play are so intense they can distort the very fabric of reality. Now, let's turn our attention to one of the most bizarre and powerful objects in the universe: magnetars. These cosmic powerhouses are a type of neutron star, but they take extreme to a whole new level. What sets magnetars apart is their unimaginably strong magnetic fields, which are trillions of times more powerful than Earth's. To put that into perspective, if a magnetar were located halfway between the Earth and the Moon, its magnetic field would erase the data from every credit card on our planet. That's how intense we're talking about. The magnetic fields of magnetars are so strong that they can literally distort the shape of atoms. Imagine an atom being stretched and squeezed like a rubber band. This is the kind of pressure we're dealing with. These forces are so extreme that they can cause the surface of the magnetar to crack, resulting in what scientists call starquakes. These starquakes release massive amounts of energy, often in the form of gamma-ray bursts, which are some of the most energetic events in the universe. But how do magnetars get such powerful magnetic fields? It all comes down to their formation. When a massive star collapses into a neutron star, its core spins incredibly fast and its magnetic field becomes concentrated and amplified. In some cases, this process creates a magnetar, a neutron star with a magnetic field so strong it defies comprehension. What's even more fascinating is that magnetars don't just sit quietly in space. They're incredibly active, emitting bursts of X-rays and gamma rays that can be detected across the universe. These bursts are so powerful that they can affect Earth's atmosphere, even from thousands of light years away. Studying magnetars helps scientists understand the limits of magnetic fields and the behavior of matter under extreme pressures. They're a reminder that the universe is full of phenomena that push the boundaries of what we thought was possible. As we move forward, we'll dive into another cosmic mystery, the pressure of dark matter and how it shapes the very fabric of the universe. Now, shifting our focus to one of the most enigmatic forces in the cosmos, let's explore the pressure of dark matter. Unlike the extreme pressures we've discussed so far, dark matter doesn't crush or distort matter in the same way. Instead, it exerts a subtle yet profound influence on the universe, shaping the very structure of galaxies. Dark matter is invisible. It doesn't emit, absorb, or reflect light, making it impossible to observe directly. Yet, its presence is undeniable. Scientists first inferred its existence by studying the rotation of galaxies. They noticed that stars on the outer edges of galaxies were moving faster than expected, as if something unseen was providing extra gravitational pull. That something is dark matter, an invisible substance that makes up about 85% of the universe's total mass. But how does dark matter exert pressure? While it doesn't interact with light or ordinary matter in the way we're familiar with, its gravitational pull creates a kind of cosmic scaffolding. This scaffolding holds galaxies together, preventing them from flying apart as they spin. Without dark matter, galaxies would lack the necessary mass to maintain their structure, and the universe as we know it would look very different. One of the biggest mysteries surrounding dark matter is its true nature. Scientists have proposed various theories, from weakly interacting massive particles or WIMP to actions, but so far, none have been definitively detected. What we do know is that dark matter's gravitational influence extends far beyond individual galaxies. It forms vast, interconnected networks called cosmic webs, which guide the formation and movement of galaxies across the universe. The pressure of dark matter isn't just a passive force, it actively shapes the cosmos. It influences the distribution of galaxies, the formation of galaxy clusters, and even the way the universe expands over time. Yet, despite its pervasive influence, dark matter remains one of the greatest unsolved puzzles in modern astrophysics. As we continue to unravel the mysteries of dark matter, we're reminded that the universe is full of invisible forces that shape its destiny. Next, we'll venture into the near-perfect vacuum of space, where pressure is almost non-existent, and explore how this emptiness contrasts with the extreme pressures we've encountered so far. Now, let's step into the vast emptiness of space, a realm where pressure takes on an entirely different character. Unlike the crushing forces we've explored in neutron stars, black holes, and even dark matter, the vacuum of space is defined by its near-total absence of pressure. In fact, space is so empty that it's often described as a near-perfect vacuum, with pressure levels so low they're almost impossible to comprehend. To put it into perspective, the pressure in space is about 1/billionth of the atmospheric pressure we experience on Earth. That means if you were to step outside a spacecraft without a spacesuit, the lack of pressure would cause your body to expand, and the air in your lungs would rush out almost instantly. It's a stark contrast to the extreme pressures we've seen in celestial bodies, where matter is compressed to unimaginable densities. But how does space achieve such a perfect vacuum? The answer lies in its sheer vastness. Space is mostly empty, with atoms and molecules spread so thinly that they rarely collide. In fact, in some regions of space, there might be only a few particles per cubic meter. Compare that to Earth's atmosphere, where trillions of particles are packed into the same space, and you begin to understand just how empty space truly is. This near-perfect vacuum has profound implications for the universe. For one, it allows light and other forms of radiation to travel vast distances without being scattered or absorbed. This is why we can see stars and galaxies billions of light-years away. Their light passes through the vacuum of space almost undisturbed. However, the vacuum of space isn't completely empty. Even in the deepest voids, there are traces of gas, dust, and cosmic rays. These particles, though sparse, play a crucial role in the formation of stars and galaxies. Over time, gravity pulls these scattered particles together, creating the dense clouds of gas and dust that eventually collapse to form new stars and planets. The vacuum of space also serves as a reminder of the universe's incredible diversity. On one hand, we have celestial bodies like neutron stars and black holes where pressure reaches unimaginable extremes. On the other, we have the vast emptiness of space where pressure is almost non-existent. Together, these extremes highlight the incredible range of conditions that exist in the cosmos. As we move forward, we'll explore how cosmic rays traveling at near light speeds create intense pressures when they collide with matter and space. This collision of extremes, emptiness and energy, shows just how dynamic and unpredictable the universe can be. Now, let's shift our focus to the high-energy realm of cosmic rays, where the vacuum of space becomes a stage for some of the most dramatic collisions in the universe. Cosmic rays are not rays in the traditional sense. They're actually high-speed particles, mostly protons and atomic nuclei, racing through space at nearly the speed of light. These particles are so energetic that when they collide with matter, they create pressures that can rival some of the most extreme conditions we've discussed so far. Imagine a single cosmic ray particle, smaller than an atom, hurtling through space with enough energy to power a small city. When this particle slams into a molecule of gas or dust, the impact is so intense that it generates shockwaves of pressure, compressing the surrounding material in an instant. These collisions are so powerful that they can even produce secondary particles, creating a cascade of energy that ripples through the surrounding space. What makes cosmic rays particularly fascinating is their origin. Some come from the sun, while others are born in the violent aftermath of supernova explosions or the chaotic environments around black holes. These particles are accelerated to such incredible speeds by magnetic fields and shockwaves in space, making them some of the fastest-moving objects in the universe. When cosmic rays collide with matter, the pressures they generate are not just physical, they're also transformative. These collisions can break apart atoms, creating new particles and even triggering nuclear reactions. In fact, cosmic rays play a key role in the formation of certain elements in space, contributing to the chemical diversity of the universe. But cosmic rays don't just affect space, they also have an impact here on Earth. When these high-energy particles reach our atmosphere, they collide with air molecules, creating showers of secondary particles that rain down on the surface. While most of these particles are harmless, they can occasionally interfere with electronics and even pose a risk to astronauts in space. The study of cosmic rays gives us a unique window into the high-energy processes that shape the universe. By understanding how these particles create intense pressures and drive cosmic transformations, we gain deeper insights into the forces that govern the cosmos. As we continue our journey, we'll explore how these same pressures play a role in the birth of stars, as vast clouds of gas and dust collapse under their own gravity. This interplay between emptiness and energy, between the vacuum of space and the explosive power of cosmic rays, reminds us just how dynamic and interconnected the universe truly is. Now, let's turn our attention to the cosmic nurseries where stars are born, vast molecular clouds scattered across the galaxy. These clouds, made up of gas and dust, are the birthplaces of stars, and the pressures within them are nothing short of extraordinary. Picture a region of space so dense that even the tiniest speck of dust is surrounded by trillions of molecules, all held together by gravity. Over time, this gravity pulls the gas and dust closer, creating pockets of increasing pressure. As these pockets grow denser, the pressure inside them rises dramatically. Imagine squeezing a balloon until it's ready to burst, except in this case, the balloon is a massive cloud of gas, and the pressure is so intense that it triggers a chain reaction. The gas and dust begin to collapse inward, heating up as they compress. This process continues until the core of the collapsing cloud reaches temperatures of millions of degrees, hot enough to ignite nuclear fusion. At this point, a new star is born. The pressure at the core of the star becomes so immense that hydrogen atoms fuse together to form helium, releasing enormous amounts of energy in the process. This energy radiates outward, counteracting the inward pull of gravity and stabilizing the star. But the story doesn't end there. The pressure within these molecular clouds doesn't just create one star, it often leads to the formation of entire star clusters, with dozens or even hundreds of stars igniting in close proximity. What's truly fascinating is how delicate this balance is. If the pressure were too low, the gas and dust would never collapse enough to ignite fusion. If it were too high, the cloud might fragment into smaller pieces, creating multiple smaller stars instead of a single massive one. This delicate interplay of pressure and gravity is what shapes the diversity of stars we see in the night sky, from tiny red dwarfs to colossal blue giants. The pressures in these molecular clouds also play a role in shaping the surrounding space. As stars form, their intense radiation and stellar winds push against the remaining gas and dust, carving out cavities and triggering new waves of star formation. It's a cosmic domino effect where the birth of one star can set off the creation of many more. By studying these processes, we gain a deeper understanding of how stars, and by extension, planets and life, come into existence. The pressures within molecular clouds are not just a force of destruction, they're a force of creation, shaping the universe one star at a time. Next, we'll explore how these same pressures can lead to even more dramatic events, such as the collisions of planets and moons, where the forces at play reshape entire worlds. The universe is full of surprises, and the story of pressure is far from over. Now, let's shift our focus to one of the most violent and transformative events in the universe: planetary collisions. Imagine two massive celestial bodies, like planets or moons, hurtling toward each other at incredible speeds. When they collide, the forces at play are beyond comprehension. The pressures generated in these impacts are so extreme that they can reshape entire worlds, leaving behind scars that last for billions of years. At the moment of impact, the pressure at the collision point reaches staggering levels. Think of it like a cosmic hammer striking an anvil, except the hammer and anvil are both the size of planets. The energy released in such an event is so immense that it creates shockwaves that ripple through both bodies, melting rock, vaporizing ice, and even altering the very structure of the planets involved. These shockwaves can travel thousands of miles, reshaping landscapes and even triggering volcanic activity. One of the most dramatic examples of this is the collision that formed our moon. Scientists believe that billions of years ago, a Mars-sized object collided with the early Earth. The pressure from this impact was so intense that it blasted a massive amount of debris into orbit, which eventually coalesced to form the moon. This event not only created our closest celestial neighbor, but also tilted Earth's axis, giving us the seasons we experience today. But planetary collisions aren't just a thing of the past. In our own solar system, evidence of such events can still be seen. For instance, the surface of Mercury is covered in massive craters, some of which were formed by impacts so powerful that they left behind cliffs hundreds of miles long. Similarly, the moons of Jupiter and Saturn bear the scars of ancient collisions, with some of their surfaces reshaped entirely by the pressures of these impacts. What's truly fascinating is how these collisions can also lead to the creation of entirely new celestial bodies. In some cases, the debris from a collision can clump together to form new moons or even planets. In others, the heat and pressure generated by the impact can melt the surfaces of the colliding bodies, creating vast oceans of molten rock that eventually cool and solidify into new landscapes. The pressures involved in planetary collisions also play a crucial role in the evolution of planetary systems. They can alter orbits, create new moons, and even strip away atmospheres. In some cases, these collisions can be so powerful that they completely obliterate one or both of the colliding bodies, leaving behind only a cloud of dust and gas. By studying these events, we gain a deeper understanding of how planets and moons form and evolve. The pressures generated in planetary collisions are not just destructive, they're also creative, shaping the universe in ways that are both violent and beautiful. Next, we'll dive into the immense pressures involved in gamma-ray bursts, the most energetic explosions in the universe. These events are so powerful that they can outshine entire galaxies, and the forces at play are truly mind-boggling. The universe never ceases to amaze, and the story of pressure continues to unfold. Now, let's turn our attention to one of the most awe-inspiring and cataclysmic events in the cosmos: gamma-ray bursts. These are not just ordinary explosions, they are the most energetic phenomena in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. The pressures involved in these bursts are so extreme that they defy imagination, and their effects ripple across the fabric of space and time. Gamma-ray bursts occur when massive stars collapse at the end of their lives or when two neutron stars collide. In both cases, the pressures generated are unimaginable. When a massive star collapses, its core is crushed into a black hole, and the surrounding material is ejected in a jet of particles moving at nearly the speed of light. The pressure within these jets is so intense that it accelerates particles to incredible energies, producing the gamma rays that give these bursts their name. The collision of two neutron stars is equally dramatic. These ultra-dense remnants of dead stars, each weighing more than our Sun but only about 12 miles across, create a gravitational field so strong that when they collide, the pressure at the point of impact is beyond comprehension. This collision not only produces a gamma-ray burst but also sends ripples through space-time itself, known as gravitational waves. The energy released in these events is so vast that it can briefly outshine entire galaxies, making gamma-ray bursts the brightest explosions in the universe. What makes gamma-ray bursts even more fascinating is their role in shaping the cosmos. The immense pressures and energies involved in these events are responsible for creating some of the heaviest elements in the universe, like gold and platinum. Without gamma-ray bursts, these precious metals might never have formed, and our universe would look very different, but the story doesn't end there. The shockwaves from gamma-ray bursts can travel across vast distances, influencing the formation of new stars and galaxies. In some cases, these bursts can strip away the atmospheres of nearby planets, rendering them uninhabitable. Yet, in others, they might provide the energy needed to trigger the birth of new stars, showcasing the dual nature of these cosmic events, both destructive and creative. By studying gamma-ray bursts, scientists gain insights into the most extreme conditions in the universe. These bursts serve as natural laboratories, allowing us to test the limits of physics and explore phenomena that cannot be replicated on Earth. The pressures involved in gamma-ray bursts are a testament to the raw power of the universe, reminding us that even in destruction there is creation. Next, we'll explore the pressures within accretion disks, the swirling rings of matter that form around black holes and neutron stars. These disks are not just beautiful to behold, they are also some of the most dynamic and energetic environments in the cosmos. The universe's story of pressure continues to unfold, revealing new wonders at every turn. Now, let's dive into the swirling chaos of accretion disks where matter meets its most extreme fate. These disks are formed when material, like gas or dust, spirals into the gravitational grip of black holes or neutron stars. But this isn't a gentle process, it's a violent, high-energy dance where pressures and temperatures reach unimaginable levels. As matter falls toward a black hole or neutron star, it doesn't plunge straight in. Instead, it forms a flattened, rotating disk around the object, known as an accretion disk. The pressure within these disks is so intense that it heats the material to millions of degrees, causing it to glow brightly across the electromagnetic spectrum. This heat isn't just a byproduct, it's a sign of the extreme forces at work. As particles collide and friction generates immense energy, the pressure in an accretion disk is driven by the sheer density of the material packed into such a small space. Imagine squeezing an entire star's worth of gas into a disk only a few million miles across. The result is a seething, turbulent environment where magnetic fields twist and snap, creating jets of particles that shoot out at nearly the speed of light. These jets are some of the most powerful phenomena in the universe, capable of traveling across millions of light years. But the story of accretion disks doesn't end with their incredible pressures. They also play a crucial role in shaping the universe. The energy released by these disks can influence the growth of galaxies, regulate star formation, and even power some of the brightest objects in the cosmos, known as quasars. In fact, without accretion disks, many of the cosmic structures we observe today might never have formed. What's truly fascinating is how these disks act as natural particle accelerators. The extreme pressures and magnetic fields within them can accelerate particles to nearly the speed of light, creating conditions that even the most advanced human-made machines can't replicate. This makes accretion disks not just cosmic wonders, but also invaluable laboratories for studying the laws of physics under the most extreme conditions. As we peel back the layers of these dynamic structures, we uncover a universe where pressure and energy are intertwined in ways that challenge our understanding. Accretion disks remind us that even in the darkest corners of space, there is light, energy, and the potential for discovery. Next, we'll explore the pressures during the inflationary period of the universe, a time when space itself expanded faster than the speed of light. The universe's story of pressure continues to unfold, revealing new mysteries at every turn. Now, let's journey back to the very beginning of the universe, to a moment so brief yet so transformative that it shaped everything we see today. This is the era of cosmic inflation, a fraction of a second after the Big Bang, when the universe expanded faster than the speed of light. But what does this rapid expansion mean for pressure, and how did it set the stage for the cosmos as we know it? During cosmic inflation, the universe wasn't just growing, it was stretching at an exponential rate, doubling in size countless times in the blink of an eye. This expansion wasn't driven by matter or energy as we understand them today, but by a mysterious force that permeated the fabric of space itself. The pressure during this period was unlike anything we can imagine, as the universe's energy density was incredibly high, creating a repulsive force that pushed space outward at an astonishing pace. Think of it like blowing up a balloon, but instead of air, the balloon is filled with an invisible, all-encompassing energy that causes it to inflate faster than light can travel. This rapid expansion didn't just stretch space, it also smoothed out the universe, ironing out any irregularities and setting the stage for the formation of galaxies, stars, and planets. Without this inflationary pressure, the universe might have remained a chaotic, uneven mess, unable to support the structures we see today. the pressures during inflation were so extreme that they left behind a faint imprint on the universe, a cosmic fingerprint known as the cosmic microwave background. This afterglow of the Big Bang carries subtle variations in temperature and density, remnants of the quantum fluctuations that were stretched to enormous scales during inflation. These tiny ripples in the early universe eventually grew into the vast cosmic web of galaxies and clusters we observe today. What's truly mind-bending is that this inflationary period lasted only a fraction of a second, yet its effects are still felt billions of years later. The pressure of cosmic inflation didn't just shape the universe, it defined the very rules of its existence, creating the conditions for gravity, matter, and energy to interact in ways that allowed life to emerge. As we reflect on this brief but pivotal moment, we're reminded that the universe's story is one of constant transformation, driven by forces that defy our everyday understanding. Cosmic inflation shows us that even in the earliest moments of existence, pressure played a starring role in shaping the cosmos. Next, we'll turn our attention to the mysterious force of dark energy, which continues to drive the universe's expansion today, exerting a pressure that challenges our understanding of space and time. The universe's story of pressure is far from over, and each chapter reveals new wonders waiting to be explored. Now, let's shift our focus to one of the most enigmatic forces in the universe: dark energy. Unlike the crushing pressures we've explored so far, dark energy operates in a way that defies our everyday understanding. It doesn't push or pull in the traditional sense. Instead, it exerts a kind of negative pressure, a force that seems to stretch the very fabric of space itself. This mysterious energy is what's driving the accelerated expansion of the universe, a phenomenon that continues to baffle scientists and reshape our understanding of cosmology. Imagine the universe as a vast, ever-growing balloon. While gravity tries to pull everything together, dark energy acts like an invisible hand, inflating the balloon faster and faster. This negative pressure isn't just a gentle push, it's a relentless force that counteracts gravity on the largest scales, causing galaxies to move away from each other at increasing speeds. In fact, without dark energy, the universe's expansion would slow down over time, but observations show the opposite is happening. The farther apart galaxies get, the faster they seem to move away from one another, a clear sign that dark energy is at work. What makes dark energy even more fascinating is its connection to the vacuum of space. In quantum physics, empty space isn't truly empty, it's teeming with virtual particles that pop in and out of existence. These fleeting particles contribute to what's known as vacuum energy, and some theories suggest that dark energy might be a manifestation of this energy. If true, it means that the very emptiness of space holds the key to the universe's expansion, a concept that challenges our deepest intuitions about how the cosmos operates. The pressure exerted by dark energy is unlike anything else in the universe. While most pressures compress or push matter together, dark energy's negative pressure does the opposite. It stretches space apart. This counterintuitive behavior is what makes dark energy so difficult to study and understand. Scientists are still grappling with questions like, what exactly is dark energy, why does it have the strength it does, and how will it shape the ultimate fate of the universe? One thing is certain: dark energy is a dominant force in the cosmos, making up roughly 68% of the universe's total energy content. Its influence is so profound that it's reshaping the large-scale structure of the universe, pulling galaxies apart and creating vast cosmic voids. As we continue to study this mysterious force, we're reminded that the universe is full of surprises, and dark energy is one of its greatest mysteries. As we ponder the role of dark energy, we're led to another incredible phenomenon: gravitational waves. These ripples in space-time, caused by massive objects like merging black holes, carry their own unique pressures, offering yet another glimpse into the universe's most extreme forces. The story of pressure in the cosmos is far from over, and each discovery brings us closer to understanding the grand tapestry of existence. Now, let's turn our attention to another extraordinary phenomenon: gravitational waves. These ripples in space-time are not just a fascinating concept. They carry immense pressures that reveal the universe's most violent and energetic events. Gravitational waves are created when massive objects, like merging black holes or neutron stars, collide or interact, sending shock waves through the very fabric of space-time itself. These waves are so powerful that they can stretch and compress matter as they pass through it, even over vast cosmic distances. Imagine space-time as a calm lake. When a massive object moves or collides, it's like dropping a boulder into the water. Ripples spread outward, distorting the surface. Gravitational waves work in a similar way, but instead of water, they distort space-time itself. The pressure involved in these waves is staggering. When two black holes merge, for example, they release energy equivalent to several times the mass of the Sun in a fraction of a second, all in the form of gravitational waves. This energy creates pressures so intense that they momentarily warp the structure of space-time, bending and squeezing everything in their path. What's truly remarkable is that these waves can travel across billions of light-years, carrying information about their origins. When they reach Earth, incredibly sensitive instruments like LIGO and Virgo can detect them, allowing scientists to study events that happened billions of years ago. The pressure exerted by gravitational waves isn't just a theoretical concept, it's something we can measure and observe, giving us a new way to explore the universe. Gravitational waves also provide a unique window into the behavior of matter under extreme conditions. For instance, when neutron stars collide, the pressures generated by the resulting gravitational waves are so immense that they can forge heavy elements like gold and platinum. These collisions are cosmic factories, producing some of the rarest materials in the universe. The pressures involved in these events are unlike anything we can recreate on Earth, making gravitational waves a key tool for understanding the limits of matter and energy. As we continue to detect and study gravitational waves, we're uncovering new insights into the universe's most extreme environments. From the collision of black holes to the merging of neutron stars, these ripples in space-time are reshaping our understanding of the cosmos. And as we explore their pressures, we're reminded once again that the universe is a place of incredible power and mystery, where even the fabric of space-time itself can bend and ripple under the weight of its most massive objects. Next, we'll dive into the pressures of the interstellar medium, the vast and dynamic regions of gas and dust that fill the spaces between stars, shaping the birth and evolution of galaxies. Now, let's shift our focus to the vast and dynamic regions of the interstellar medium, the cosmic canvas where stars are born. This sprawling expanse of gas and dust filling the spaces between stars is far from empty. It's a bustling arena of pressure and motion that plays a crucial role in shaping the universe as we know it. The interstellar medium is a delicate balance of forces where gravity, radiation, and magnetic fields interact to create the conditions for star formation. At first glance, the interstellar medium might seem like a serene void, but it's anything but calm. The gas and dust here are constantly under pressure, both from within and from external forces. Gravity pulls matter together, creating dense clouds where stars can form, while radiation from nearby stars and supernova pushes back, heating and dispersing the gas. This tug-of-war between compression and expansion is what drives the cycle of star birth and death. One of the most fascinating aspects of the interstellar medium is its ability to collapse under its own gravity. When a region of gas and dust becomes dense enough, the pressure from gravity overcomes the outward pressure of heat and radiation, causing the cloud to collapse. As it collapses, the pressure inside increases, heating the material until nuclear fusion ignites and a new star is born. This process is how stars like our Sun come into existence, and it's all thanks to the intricate pressures at work in the interstellar medium. But the interstellar medium isn't just a passive backdrop, it's an active participant in the life cycle of galaxies. Shockwaves from supernova explosions, for example, can compress nearby gas clouds, triggering the formation of new stars. These shockwaves create regions of intense pressure where the interstellar medium is squeezed and heated, setting the stage for the next generation of stars. In this way, the interstellar medium acts as a cosmic recycling system, turning the remnants of dying stars into the building blocks of new ones. The pressures in the interstellar medium also play a key role in shaping the structure of galaxies. In spiral galaxies like our Milky Way, the interstellar medium forms intricate patterns of gas and dust, creating the iconic arms that wind around the galactic center. These regions are where star formation is most active, as the pressure from the galaxy's rotation and magnetic fields compresses the gas, sparking the birth of countless stars. As we explore the pressures of the interstellar medium, we gain a deeper understanding of how the universe creates and sustains its most luminous objects. From the birth of stars to the evolution of galaxies, the interstellar medium is a vital player in the cosmic drama. And as we continue to study its pressures, we uncover new insights into the forces that shape the universe, reminding us that even the spaces between stars are teeming with life and energy. Next, we'll journey to the cores of rocky planets like Earth, where unimaginable pressures transform solid iron into a swirling, molten sea, shaping the very foundations of these worlds. Now, let's turn our attention inward to the very heart of rocky planets like Earth. Deep beneath the surface, where the weight of the entire planet presses down, lies a realm of unimaginable pressure. Here, in the cores of these worlds, solid iron is transformed into a swirling, molten sea, shaping the very foundations of the planet itself. At the core of Earth, the pressure reaches staggering levels millions of times greater than the atmospheric pressure we experience on the surface. This immense force is created by the sheer weight of the planet's layers pressing inward, compressing the materials at the center to their absolute limits. Under such extreme conditions, even solid iron, one of the strongest and most durable metals, cannot maintain its rigid structure. Instead, it melts into a liquid state, forming a dynamic, churning core. This molten core isn't just a static pool of metal, it's a vital engine that drives many of Earth's most important processes. The movement of this liquid iron generates Earth's magnetic field, a protective shield that deflects harmful solar radiation and cosmic rays. Without this magnetic field, life as we know it might not exist, as the surface would be bombarded by dangerous particles from space. The pressure at the core, therefore, isn't just a scientific curiosity, it's a key factor in making Earth a habitable planet. But the pressures at planetary cores aren't unique to Earth. Other rocky planets like Mercury, Venus, and Mars also have cores subjected to extreme compression, though the specifics vary depending on the planet's size and composition. For example, Mars, being smaller than Earth, has a core that may have cooled and solidified over time, while Venus, with its similar size, likely retains a molten core much like our own. These differences in core pressure and state play a significant role in shaping each planet's geology, atmosphere, and potential for supporting life. The study of planetary cores also offers clues about the formation and evolution of rocky planets. Scientists believe that the intense pressures at the core are a remnant of the planet's early history, when it was still forming from a cloud of dust and gas. As the planet grew, the pressure at its center increased, eventually reaching the point where iron could no longer remain solid. This process not only shaped the core but also influenced the planet's overall structure, from its mantle to its crust. As we explore the pressures of planetary cores, we gain a deeper appreciation for the forces that shape the worlds around us. From generating magnetic fields to influencing planetary evolution, the extreme pressures at the heart of rocky planets are a testament to the dynamic and ever-changing nature of the universe. Next, we'll venture into the realm of stellar winds, where streams of charged particles create pressures that shape the lives of stars and their surrounding environments. Now, let's shift our gaze outward beyond the confines of planetary cores and into the vast expanse of space where stars unleash their power. Stellar winds, the streams of charged particles ejected from stars, create pressures that shape not only the stars themselves but also the environments around them. These winds are far from gentle breezes. They are powerful forces that can sculpt entire star systems and influence the birth and death of stars. At the heart of a star, nuclear fusion generates immense energy, heating the outer layers to extreme temperatures. This heat causes the star's outer atmosphere to expand and escape into space, forming a continuous flow of charged particles known as stellar wind. The pressure exerted by these winds can be staggering, especially in massive stars, where the winds are so intense they can strip away the outer layers of nearby planets or even other stars. For example, our own Sun produces a steady stream of solar wind, which, while relatively mild compared to more massive stars, still exerts enough pressure to push against the interstellar medium, creating a protective bubble known as the heliosphere. This bubble shields our solar system from much of the cosmic radiation that permeates space, playing a crucial role in maintaining a stable environment for life on Earth. In more massive stars, such as Wolf-Rayet stars, the pressure of stellar winds is even more extreme. These stars eject material at speeds of millions of miles per hour, creating winds so powerful they can carve out vast cavities in surrounding gas clouds. These cavities, filled with hot, ionized gas, become the birthplaces of new stars as the pressure from the winds compresses nearby gas and dust, triggering the collapse that leads to star formation. But stellar winds don't just shape the cosmos, they also play a key role in the life cycle of stars themselves. As a star ages and exhausts its nuclear fuel, its stellar winds can strip away its outer layers, exposing the core and leading to dramatic transformations. In some cases, this process results in the formation of planetary nebulae, where the expelled material glows brightly, illuminated by the dying star at its center. In others, it sets the stage for a supernova as the star's core collapses under its own gravity, releasing an explosion that outshines entire galaxies. The pressure of stellar winds is a reminder of the dynamic and interconnected nature of the universe. From shaping star systems to influencing the birth and death of stars, these winds are a testament to the immense forces at work in the cosmos. Next, we'll explore the low-pressure regions of cosmic voids, where matter is sparse and galaxies are few and far between, offering a stark contrast to the intense pressures we've just examined. Now, let's journey into the vast emptiness of cosmic voids, regions of space where the pressure is almost non-existent, and matter is spread so thin that galaxies are few and far between. These voids are the opposite of the intense pressures we've explored so far, offering a fascinating contrast to the densely packed environments of stars, black holes, and galactic clusters. Cosmic voids are enormous, stretching hundreds of millions of light-years across, and they make up a significant portion of the universe's large-scale structure. Within these voids, the density of matter is incredibly low, with only a handful of galaxies scattered across their expanse. This scarcity of matter creates an environment where pressure is minimal, almost approaching the near-perfect vacuum of space. The formation of cosmic voids is tied to the early universe. During the Big Bang, tiny fluctuations in density led to regions where matter clumped together, forming galaxies and galaxy clusters, while other regions were left nearly empty. Over billions of years, gravity pulled matter into denser regions, leaving behind these vast, empty voids. Despite their emptiness, cosmic voids play a crucial role in shaping the universe. They act as the backdrop against which galaxies and galaxy clusters are distributed, forming a cosmic web of filaments and nodes. The low pressure within these voids also influences the movement of galaxies, as they tend to flow away from the voids and toward denser regions of space. Interestingly, cosmic voids are not entirely empty. They contain trace amounts of gas, dark matter, and even the occasional isolated galaxy. These sparse elements are often remnants of the early universe, offering astronomers a unique window into the conditions that existed billions of years ago. The study of cosmic voids also provides insights into dark energy, the mysterious force driving the accelerated expansion of the universe. Because voids are less dense, they expand faster than regions filled with matter, making them ideal laboratories for testing theories about dark energy and the universe's overall structure. Cosmic voids remind us that the universe is not just a collection of stars and galaxies, but also a tapestry of emptiness, where the absence of matter tells its own story. Next, we'll turn our attention to the pressures within star clusters, where thousands of stars are packed into a small region of space, creating a dynamic and crowded environment. Now, let's shift our focus to one of the most cataclysmic events in the universe, the collision of neutron stars. When two of these incredibly dense objects spiral toward each other and finally collide, the pressures involved are beyond comprehension. These collisions are so powerful that they ripple through the fabric of spacetime itself, sending out gravitational waves that can be detected billions of light years away. Neutron stars are already among the most extreme objects in the cosmos, with densities so high that a single teaspoon of their material would weigh billions of tons. When two neutron stars collide, the pressures at the moment of impact are unimaginable. The cores of these stars are compressed even further, reaching densities that defy our understanding of physics. This extreme pressure creates conditions where matter is forced into exotic states, and heavy elements like gold, platinum, and uranium are forged in the fiery aftermath. The collision doesn't just produce heavy elements, it also generates an intense burst of energy in the form of light, gamma rays, and gravitational waves. These gravitational waves, first detected in 2017, provide scientists with a new way to study the universe. They reveal details about the masses, spins, and distances of the colliding neutron stars, offering insights into the nature of these extreme objects. Interestingly, the collision of neutron stars also creates a phenomenon known as a kilonova, a brilliant explosion that outshines entire galaxies for a brief moment. This explosion is fueled by the radioactive decay of the heavy elements produced in the collision, and it leaves behind a glowing remnant that astronomers can study for years. The pressures involved in neutron star collisions are so extreme that they push the boundaries of our understanding of physics. These events not only create some of the universe's most precious elements, but also provide a unique laboratory for testing theories about gravity, matter, and the fundamental forces of nature. As we continue our journey through the universe's most extreme pressures, we'll next explore the even more powerful phenomenon of hypernova, where the pressures are so intense that they dwarf even those of neutron star collisions. Now, let's turn our attention to an event that makes even neutron star collisions seem tame: hypernova. These colossal explosions are the universe's way of showing off its raw power, and the pressures involved are nothing short of mind-bending. Hypernova occur when massive stars, many times heavier than our Sun, reach the end of their lives and collapse under their own gravity. Unlike regular supernova, hypernova are so energetic that they release up to 100 times more energy, making them some of the most violent events in the cosmos. At the heart of a hypernova lies an unimaginable pressure. As the star's core collapses, it creates a black hole or a rapidly spinning neutron star known as a magnetar. The gravitational forces at play are so intense that they crush matter into densities far beyond what we see in neutron stars. This extreme pressure triggers a shockwave that rips through the star's outer layers, blasting them into space at incredible speeds. The result is an explosion so bright that it can outshine an entire galaxy for weeks. What makes hypernova truly fascinating is the role they play in shaping the universe. The immense pressures generated during these explosions are responsible for creating some of the heaviest elements in existence, such as gold, platinum, and uranium. These elements are then scattered across the cosmos, eventually becoming part of new stars, planets, and even life itself. Hypernova also produce another extraordinary phenomenon, gamma-ray bursts. These are the most energetic bursts of light in the universe, lasting from a few milliseconds to several minutes. The pressures involved in generating these bursts are so extreme that they can warp space-time itself, creating ripples that travel across the universe. The study of hypernova has given scientists a deeper understanding of the life cycles of massive stars and the extreme conditions that exist in the universe. These events push the boundaries of our knowledge, challenging us to rethink our understanding of gravity, matter, and the forces that govern the cosmos. As we move forward, we'll explore another cosmic phenomenon where pressures reach even greater extremes, the mysterious and powerful quasars, which are fueled by supermassive black holes at the centers of galaxies. Now, let's shift our focus to another cosmic marvel where pressures reach staggering levels, pulsars. These rapidly spinning neutron stars are not only remnants of massive stellar explosions, but also some of the most extreme objects in the universe. Pulsars are born from the same cataclysmic events that create neutron stars, but what sets them apart is their incredible rotation speed and the intense magnetic fields they possess. At the core of a pulsar, the pressure is so immense that it crushes matter into a state far denser than anything found on Earth. A single teaspoon of material from a pulsar would weigh billions of tons. This extreme density is a result of gravity overpowering all other forces, compressing protons and electrons into neutrons. But what truly makes pulsars unique is their rapid spin. Some pulsars rotate hundreds of times per second, creating forces so powerful that they emit beams of radiation from their magnetic poles. These beams sweep across the cosmos like cosmic lighthouses, and when they align with Earth, we detect them as regular pulses of light, radio waves, or even X-rays. The pressure required to generate these beams is unimaginable, as the magnetic fields of pulsars can be trillions of times stronger than Earth's. This combination of rapid rotation and intense magnetic fields creates an environment where matter is stretched, twisted, and accelerated to near light speeds. The pressures within pulsars also give rise to fascinating phenomena such as starquakes. These are sudden shifts in the pulsar's crust caused by the immense stress of its rotation and magnetic fields. When a starquake occurs, it releases energy equivalent to millions of nuclear bombs, sending ripples through the fabric of space-time. Pulsars are not just cosmic curiosities, they are also invaluable tools for scientists. Their precise pulses allow astronomers to study the effects of extreme gravity, test theories of relativity, and even map the structure of our galaxy. The pressures within pulsars push the boundaries of our understanding, revealing the incredible forces at work in the universe. As we continue our journey, we'll delve into another realm of extreme pressures, the atmospheres of exoplanets, where conditions can be so intense that they defy imagination. Now, let's venture into the atmospheres of distant worlds, where the pressures are so extreme they defy even the wildest imaginations. Exoplanets, planets orbiting stars outside our solar system, host some of the most bizarre and hostile environments in the universe. Among these, certain exoplanets have atmospheres so dense and intense that they create conditions unlike anything we've ever seen on Earth. Take, for example, the exoplanet known as WASP-76b. This scorching hot world orbits so close to its star that its dayside temperatures soar to over 2,000 degrees Celsius. The immense heat vaporizes metals like iron, which are then carried by supersonic winds to the cooler night side. There, the pressure and temperature drop dramatically, causing the iron to condense and fall as molten rain. Imagine a world where the skies rain liquid metal, This is the kind of extreme pressure we're talking about. But it's not just molten metal that makes exoplanet atmospheres so fascinating. On planets like HD 189733b, winds whip through the atmosphere at speeds exceeding 8,000 kilometers per hour. These winds are driven by the extreme pressure differences between the day and night sides, creating a chaotic and turbulent environment. The pressure in these atmospheres can be thousands of times greater than Earth's, compressing gases into exotic states and creating conditions that challenge our understanding of planetary science. Some exoplanets, like GJ1214b, are shrouded in thick, steamy atmospheres composed mostly of water vapor. The pressure here is so high that water exists in a supercritical state, a strange phase where it's neither liquid nor gas but something in between. This supercritical water can dissolve materials like rock, creating a bizarre, soupy environment that's both fascinating and terrifying. These extreme pressures don't just shape the atmospheres of exoplanets, they also influence their potential for life. While some worlds are too hostile to support life as we know it, others might harbor conditions that, while extreme, could still allow for the existence of exotic forms of life. The study of exoplanet atmospheres opens a window into the incredible diversity of planetary systems and the extreme pressures that govern them. As we move forward, we'll explore another cosmic phenomenon where pressure plays a pivotal role: the collisions of galaxies, where immense forces reshape the very fabric of the universe. Now, let's shift our gaze to a phenomenon that reshapes the very fabric of the cosmos: galactic collisions. When galaxies collide, the pressures involved are so immense that they can trigger bursts of star formation and completely alter the structure of the universe on a grand scale. These collisions are not quick, violent crashes, but rather slow, majestic dances that unfold over millions or even billions of years. During a galactic collision, the gravitational forces between two galaxies pull them together, creating immense pressure in the gas and dust clouds within them. This pressure compresses the material, heating it up and causing it to collapse under its own gravity. As these clouds collapse, they ignite the birth of new stars in a process known as starburst activity. The pressure is so intense that it can lead to the formation of thousands or even millions of stars in a relatively short cosmic timescale. One of the most famous examples of this is the Antennae galaxies, a pair of colliding galaxies located about 60 million light-years away. As they merge, the pressure from their interaction has triggered a massive wave of star formation, creating bright, young star clusters scattered throughout the collision zone. The pressure here is so extreme that it not only forms stars but also distorts the shapes of the galaxies, stretching them into long, sweeping tails of gas and dust. But the pressure doesn't stop at star formation. Galactic collisions also generate shock waves that ripple through the interstellar medium, compressing gas and dust even further. These shock waves can create regions of incredibly high pressure, where new stars and even entire star clusters are born. Over time, the galaxies involved in the collision will eventually merge into a single, larger galaxy, their structures reshaped by the immense pressures they've endured. Interestingly, these collisions also play a crucial role in the evolution of supermassive black holes. As galaxies merge, their central black holes are drawn together by gravity, eventually spiraling inward and merging themselves. The pressure and energy released during this process can produce some of the most powerful gravitational waves in the universe, rippling through space-time itself. Galactic collisions remind us that the universe is a dynamic, ever-changing place, where even the largest structures are shaped by the forces of pressure and gravity. As we continue our journey, we'll explore another cosmic marvel where pressure takes center stage: the luminous cores of distant galaxies known as quasars, where supermassive black holes unleash unimaginable energy. Now, let's turn our attention to one of the most dazzling and energetic phenomena in the universe: quasars. These luminous cores of distant galaxies are powered by supermassive black holes, and the pressures within them are nothing short of mind-bending. Quasars shine with the brightness of trillions of stars, outshining entire galaxies, and their brilliance is fueled by the immense pressures generated as matter spirals into the black hole at their center. At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. As gas, dust, and even stars are pulled toward the black hole, they form a swirling disk of material known as an accretion disk. The pressure within this disk is so extreme that friction heats the material to millions of degrees, causing it to glow intensely across the electromagnetic spectrum. This process releases staggering amounts of energy, making quasars some of the brightest objects in the universe. The pressure in the accretion disk doesn't just create light, it also generates powerful magnetic fields and jets of particles that shoot out from the poles of the black hole at nearly the speed of light. These jets can extend for thousands of light years, carving through the surrounding space and influencing the evolution of the galaxy itself. The pressure driving these jets is so immense that it can shape the structure of entire galactic neighborhoods, pushing gas and dust aside and even triggering star formation in distant regions. Interestingly, the pressure within quasars also plays a key role in regulating the growth of the supermassive black hole itself. As matter falls into the black hole, the intense pressure and radiation from the accretion disk can push some of the material away, creating a balance between inflow and outflow. This feedback mechanism ensures that the black hole doesn't grow too quickly, maintaining a delicate cosmic equilibrium. Quasars are not just fascinating in their own right, they also serve as cosmic beacons, helping astronomers study the early universe. Because quasars are so bright, they can be seen from billions of light years away, offering a glimpse into the conditions of the universe when it was young. The pressures within these ancient quasars reveal how supermassive black holes and galaxies evolved over time, shaping the cosmos as we know it today. As we continue our exploration of extreme pressures in the universe, we'll next delve into the mysterious world of cosmic dust, where particles are compressed into new stars and planets, continuing the cycle of creation and destruction that defines our universe. Now, let's shift our gaze to the quieter, yet equally fascinating corners of the universe, cosmic dust clouds. These vast, shadowy regions may seem unremarkable at first glance, but they are the birthplaces of stars and planets where the pressures at work are both subtle and profound. Cosmic dust clouds, also known as molecular clouds, are made up of tiny particles of gas and dust, often no larger than a grain of sand. Yet within these clouds, the forces of gravity and pressure conspire to create something extraordinary. As gravity pulls these particles together, the pressure within the cloud begins to rise. Over time, this pressure compresses the gas and dust into denser clumps, forming the seeds of future stars and planets. The process is slow, taking millions of years, but the pressures involved are immense. In some regions, the pressure becomes so great that it triggers the collapse of the cloud, leading to the formation of protostars, the earliest stage of a star's life. These protostars continue to grow as more material is drawn in, increasing the pressure at their cores until nuclear fusion ignites and a new star is born. But the story doesn't end there. The same pressures that create stars also shape the planets that orbit them. As the star forms, the surrounding dust and gas begin to swirl into a disk known as a protoplanetary disk. Within this disk, particles collide and stick together, gradually building up into larger bodies. The pressure within the disk helps to compact these particles, forming planetesimals, the building blocks of planets. Over time, these planetesimals grow into full-fledged planets, shaped by the relentless pressures of their cosmic environment. Interestingly, the pressure within cosmic dust clouds isn't uniform. Variations in density and temperature create pockets of higher and lower pressure, leading to the formation of stars and planets of different sizes and compositions. In some regions, the pressure is so extreme that it gives rise to massive stars, many times larger than our Sun. In others, the pressure is just right for the formation of smaller, rocky planets like Earth. Cosmic dust clouds are more than just nurseries for stars and planets. They are also the sites of incredible beauty. When illuminated by nearby stars, these clouds can glow with vibrant colors, creating some of the most stunning sights in the universe. The pressures within them may be invisible to the naked eye, but their effects are written across the cosmos, shaping the very fabric of space and time. As we continue our journey through the universe's most extreme pressures, we'll next explore the explosive power of stellar flares, where the pressures generated can rival even the most violent events in the cosmos. Now, let's turn our attention to one of the most dramatic displays of cosmic power, stellar flares. These explosive eruptions of energy from stars are not just dazzling light shows. They are also a testament to the immense pressures at play in the universe. Stellar flares occur when the magnetic fields of a star become twisted and unstable, releasing vast amounts of energy in a matter of minutes. The pressures generated during these events are staggering, often rivaling the most violent phenomena in the cosmos. When a stellar flare erupts, it sends out a burst of radiation, including X-rays and ultraviolet light, that can travel across vast distances. The pressure within the flare itself is so intense that it can heat the surrounding plasma to millions of degrees, creating a shockwave that ripples through space. These shockwaves can compress nearby gas and dust, triggering new waves of star formation or even disrupting the orbits of planets. In some cases, the pressure from a stellar flare can strip away the atmosphere of a nearby planet, leaving it barren and lifeless. But what causes these magnetic fields to become so unstable in the first place? The answer lies deep within the star itself. In stars like our Sun, the intense heat and pressure at the core generate powerful magnetic fields. These fields are constantly shifting and interacting, creating regions of high tension. When the tension becomes too great, the magnetic fields snap, releasing their stored energy in the form of a flare. The pressure released during this process is so immense that it can briefly outshine the star itself, making the flare visible from incredible distances. Interestingly, not all stellar flares are created equal. Smaller stars, known as red dwarfs, are particularly prone to frequent and powerful flares. These stars have stronger magnetic fields relative to their size, which means they can produce flares that are far more intense than those of larger stars. The pressure generated by these flares can have a profound impact on any planets orbiting the star, potentially sterilizing them or even tearing them apart. Stellar flares are a reminder of the dynamic and often violent nature of the universe. They show us that even the seemingly stable stars we see in the night sky are capable of unleashing unimaginable forces. As we continue our exploration of the universe's most extreme pressures, we'll next delve into the intricate structures of planetary rings, where the pressures of countless collisions create some of the most beautiful and complex formations in space. Now, shifting our gaze from the explosive energy of stellar flares, let's explore the delicate yet dynamic world of planetary rings. These stunning structures, like those surrounding Saturn, are not just beautiful to behold, they are also a fascinating study in the pressures of space. Planetary rings are made up of countless particles, ranging from tiny grains of dust to massive boulders, all orbiting a planet in a delicate balance of gravity and motion. But what keeps these particles from simply clumping together or drifting apart? The answer lies in the intricate interplay of pressures within the rings. The pressure within planetary rings is primarily driven by collisions. As particles orbit the planet, they constantly collide with one another, creating a chaotic yet organized system. These collisions generate pressure that prevents the particles from coalescing into larger bodies, while also keeping them from dispersing into space. The result is a thin, flat disk of material that can stretch for thousands of miles, yet is often only a few meters thick. The pressure from these collisions is so finely tuned that it allows the rings to maintain their structure over millions of years. One of the most striking examples of this phenomenon is Saturn's rings. These iconic rings are composed of billions of icy particles, each moving at incredible speeds. The pressure from their collisions creates intricate patterns such as gaps, waves, and braids that are shaped by the gravitational influence of Saturn's moons. For instance, the Cassini division, a prominent gap in Saturn's rings, is caused by the gravitational pull of the moon Mimas. The pressure within the rings responds to these external forces, creating a dynamic and ever-changing system. But the pressures in planetary rings aren't just about collisions. They also involve the subtle influence of electromagnetic forces and the planet's magnetic field. In Saturn's case, the planet's strong magnetic field interacts with the charged particles in the rings, creating additional pressure that shapes their structure. This interplay of forces makes planetary rings one of the most complex and fascinating systems in the solar system. Interestingly, not all planetary rings are the same. While Saturn's rings are the most famous, other gas giants like Jupiter, Uranus, and Neptune also have rings, each with their own unique pressures and structures. For example, Jupiter's rings are much fainter and composed of darker material, while Uranus's rings are tilted at an extreme angle, creating a completely different set of pressures and dynamics. These variations remind us that even within the same category of celestial objects, the universe finds endless ways to surprise us. As we marvel at the beauty and complexity of planetary rings, we're reminded of the delicate balance of forces that shape our universe. From the explosive pressures of stellar flares to the subtle collisions in Saturn's rings, these phenomena reveal the incredible diversity of cosmic pressures. Next, we'll venture into the vast expanses of intergalactic gas, where the pressures of space take on an entirely different form. Now, let's journey beyond the confines of our solar system and into the vast, almost empty spaces between galaxies. Here, in the realm of intergalactic gas, the pressures are unlike anything we've explored so far. Intergalactic gas is the diffuse material that fills the voids between galaxies, a thin and wispy medium that plays a crucial role in the structure and evolution of the universe. While it might seem like empty space, this gas is far from inert. It's a dynamic and essential component of the cosmic web. The pressure of intergalactic gas is incredibly low compared to the crushing forces we've seen in neutron stars or black holes, but it's still significant in its own way. This gas is so diffuse that its density is often just a few atoms per cubic meter, making it millions of times less dense than the air we breathe. Yet, even in this sparse environment, pressure exists. It's driven by the heat of the gas, which can reach temperatures of millions of degrees, and by the gravitational pull of nearby galaxies and dark matter. These forces create a delicate balance, shaping the flow and distribution of the gas across the cosmos. One of the most fascinating aspects of intergalactic gas is its role in the formation of galaxies. As galaxies grow and evolve, they pull in this gas, using it as fuel to form new stars. The pressure of the gas determines how easily it can be drawn into galaxies and how it interacts with the magnetic fields and cosmic rays that permeate space. In some cases, the pressure is so low that the gas flows smoothly into galaxies, feeding their growth. In others, the pressure can create shock waves, heating the gas and preventing it from collapsing into stars. This interplay of pressure and motion is a key factor in the life cycle of galaxies. But intergalactic gas isn't just a passive player. It's also a record of the universe's history. As light from distant galaxies passes through this gas, it leaves behind a fingerprint, revealing the composition and temperature of the material. Astronomers use this information to map the distribution of intergalactic gas and to study the large-scale structure of the universe. The pressure of this gas has shaped the cosmic web, the intricate network of filaments and voids that connects galaxies across billions of light years. Interestingly, the pressure of intergalactic gas isn't uniform. In some regions, the gas is compressed by the gravitational pull of galaxy clusters, creating pockets of higher pressure. In others, the gas is stretched thin, forming vast voids where pressure is almost non-existent. These variations remind us that even in the seemingly empty spaces between galaxies, the universe is full of complexity and motion. As we explore the pressures of intergalactic gas, we're reminded of the interconnectedness of the cosmos. From the dense cores of stars to the sparse voids between galaxies, pressure shapes the universe in ways both subtle and profound. Next, we'll turn our attention to the pressures within star clusters, where thousands of stars are packed into a small region of space, creating a unique and dynamic environment. Now, shifting our focus to the bustling neighborhoods of the cosmos, let's dive into the pressures found within star clusters. These clusters are like cosmic cities, where thousands of stars are crammed into a relatively small region of space. Imagine the energy and activity of a crowded metropolis, but on a scale that defies comprehension. The pressure within these clusters is shaped by the gravitational pull of so many stars packed so closely together, creating a dynamic and often chaotic environment. In star clusters, the pressure isn't just about gravity, it's also about the interactions between stars. As these stars orbit one another, their gravitational forces tug and pull, creating a constant push and pull that shapes the cluster's structure. This gravitational dance can lead to close encounters where stars pass near each other, sometimes even colliding or exchanging material. These interactions generate immense pressure, both gravitational and thermal, as the stars heat up and release energy into their surroundings. One of the most striking features of star clusters is their density. In some clusters, stars are packed so tightly that the distance between them can be just a few light years, compared to the tens or hundreds of light years that separate stars in less crowded regions of space. This density creates a unique pressure environment where the gravitational influence of each star affects its neighbors, leading to complex and ever-changing dynamics. Over time, these pressures can cause stars to migrate within the cluster, with some being ejected entirely, while others settle into stable orbits. The pressure within star clusters also plays a crucial role in their evolution. In younger clusters, the pressure is often higher as the stars are still settling into their orbits and interacting more frequently. Over millions or even billions of years, the pressure gradually decreases as stars are lost to the surrounding galaxy or as the cluster expands. This process shapes the cluster's lifespan, determining whether it will remain tightly bound or eventually dissolve into the wider galaxy. Interestingly, the pressure in star clusters isn't uniform. In the core of the cluster, where stars are most densely packed, the pressure is at its highest. Here, stars are constantly jostling for position, and the gravitational forces are at their most intense. Moving outward, the pressure decreases, creating a gradient that influences how stars move and interact. This variation in pressure can even affect the types of stars that form within the cluster, with more massive stars tending to settle in the core, while lighter stars are pushed to the outskirts. As we explore the pressures within star clusters, we gain a deeper appreciation for the complexity of these cosmic communities. They are not just random collections of stars, they are dynamic systems shaped by the interplay of gravity, motion, and pressure. Next, we'll venture into the largest structures in the universe, where pressure plays a key role in connecting galaxies across vast distances. Now, let's stretch our imagination to the grandest scales of the universe as we explore the pressures within cosmic filaments. These colossal structures are the backbone of the cosmos, weaving a vast web that connects galaxies across unimaginable distances. Picture them as the cosmic highways, threading through the emptiness of space and binding the universe together in an intricate network. Cosmic filaments are made up of dark matter and gas, forming long, thin strands that stretch for hundreds of millions of light years. The pressure within these filaments is shaped by the gravitational pull of the matter they contain, as well as the forces exerted by the galaxies they connect. While the pressure here is far less intense than in the cores of stars or black holes, It plays a crucial role in shaping the large-scale structure of the universe. One of the most fascinating aspects of cosmic filaments is how they channel matter across the cosmos. Gas flows along these filaments, pulled by gravity toward the denser regions where galaxies and galaxy clusters form. This flow creates a dynamic pressure environment where the movement of matter generates forces that can influence the growth and evolution of galaxies. In a way, cosmic filaments act as cosmic rivers, guiding the raw materials needed for star formation and galaxy building. The pressure within these filaments also affects the distribution of dark matter, which makes up the majority of their mass. Dark matter doesn't interact with light, but its gravitational influence shapes the filaments and determines how galaxies are distributed along them. This interplay between dark matter and gas creates a delicate balance of pressures, maintaining the stability of these vast structures over billions of years. Interestingly, the pressure in cosmic filaments isn't uniform. Near the intersections of filaments where galaxy clusters form, the pressure is higher due to the concentration of matter. These regions, known as nodes, are some of the most massive and energetic places in the universe. In contrast, the thinner, more diffuse parts of the filaments experience lower pressure, allowing gas to flow more freely along their length. As we consider the pressures within cosmic filaments, we gain a deeper understanding of how the universe is organized on the largest scales. These filaments are not just passive structures, they are dynamic, evolving pathways that shape the destiny of galaxies and the cosmos itself. Next, we'll delve into the pressures within neutron stars, where the forces at play are as extreme as they come. Now, shifting our focus to the incredible forces at play within neutron stars, let's explore the phenomenon of neutron star quakes. These cosmic events are unlike anything we experience on Earth, as they occur under conditions of unimaginable pressure and density. Neutron stars, the remnants of massive stars that have exploded in supernova, are so dense that a single teaspoon of their material would weigh billions of tons. This extreme density creates a crust on the surface, but even this crust isn't immune to the immense forces at work. Neutron star quakes happen when the crust of the star, under the strain of its own gravity and the intense magnetic fields, suddenly cracks and shifts. The pressure within the crust is so extreme that even a small fracture can release an enormous amount of energy, equivalent to a magnitude 10 earthquake or stronger. These quakes are so powerful that they can cause the entire star to vibrate, sending ripples through spacetime itself. The pressure inside a neutron star is so intense that the crust is made up of a lattice of atomic nuclei, packed together in a way that defies normal physics. When a quake occurs, the crust fractures and the material beneath, a superfluid of neutrons, flows and adjusts to the new conditions. This movement generates shockwaves that travel through the star, sometimes even altering its rotation speed or emitting bursts of X-rays and gamma rays. What makes neutron star quakes particularly fascinating is how they reveal the internal structure of these mysterious objects. By studying the vibrations and energy released during a quake, scientists can learn more about the properties of neutron star matter, which exists in states that cannot be replicated on Earth. These quakes also provide clues about the star's magnetic field, which can be trillions of times stronger than Earth's, adding to the immense pressures that cause the crust to crack. Neutron star quakes remind us that even in the most extreme environments, matter is constantly in motion, shaped by forces beyond our everyday experience. As we continue to unravel the mysteries of these cosmic powerhouses, we gain a deeper appreciation for the incredible pressures that shape the universe. Next, we'll turn our attention to the powerful jets ejected by black holes, where pressures reach even more astonishing levels. Now, let's venture into the realm of black hole jets, where the universe showcases yet another display of its most extreme pressures. These jets are among the most energetic phenomena in the cosmos, launching streams of particles at nearly the speed of light. But what creates such incredible forces, and how do they shape the surrounding space? Black hole jets form when matter spirals into a black hole, but not all of it crosses the event horizon. Some of this material gets funneled into powerful magnetic fields, which act like cosmic particle accelerators. These fields channel the matter into narrow beams, propelling it outward at velocities so high that they approach the speed of light. The pressure within these jets is staggering, as the particles are compressed and accelerated to unimaginable energies. The process begins in the accretion disk, a swirling ring of gas and dust that orbits the black hole. As the material in the disk heats up and spirals inward, it generates intense magnetic fields. These fields twist and snap, launching jets of charged particles perpendicular to the disk. The pressure within these jets is so extreme that it can push through the surrounding interstellar medium, carving out vast cavities in space and even influencing the formation of galaxies. What's truly remarkable is the sheer scale of these jets. They can stretch for thousands or even millions of light years, far beyond the boundaries of their host galaxies. The pressure within the jets not only propels particles outward but also generates intense radiation, including X-rays and gamma rays, which can be detected across the universe. These jets are so powerful that they can outshine entire galaxies, making them some of the brightest objects in the cosmos. Scientists believe that black hole jets play a crucial role in shaping the universe. By redistributing energy and matter across vast distances, they influence the growth of galaxies and the evolution of cosmic structures. The pressures within these jets also provide a unique laboratory for studying the behavior of matter under extreme conditions, offering insights into the fundamental laws of physics. As we marvel at the power of black hole jets, we're reminded once again of the incredible forces at work in the universe. These jets are not just streams of particles, they are cosmic engines, driving change and shaping the fabric of space itself. Next, we'll explore the pressures within protostars, where the seeds of new stars are born under the crushing weight of gravity. Now, let's turn our attention to the birthplaces of stars, where the universe begins its most delicate yet powerful act of creation. Protostars, the early stages of star formation, are cosmic nurseries where immense pressures shape the future of entire solar systems. Here, vast clouds of gas and dust collapse under the relentless pull of gravity, setting the stage for the birth of a new star. As these clouds collapse, the pressure within them begins to rise dramatically. Gravity pulls the gas inward, compressing it into a denser and denser core. This process generates incredible heat, causing the core to glow faintly as it gathers more material. The pressure at the heart of a protostar is so intense that it can reach millions of times the pressure found on Earth's surface. This crushing force is what ultimately ignites the nuclear fusion that will power the star for billions of years. But the journey from a collapsing gas cloud to a fully formed star is far from straightforward. The pressure within the protostar must balance the outward push of heat and radiation generated by the collapsing material. If this balance is disrupted, the protostar may fragment, leading to the formation of multiple stars or even star systems. This delicate interplay between gravity and pressure is what makes protostars such fascinating objects of study. One of the most remarkable aspects of protostars is their ability to shape their surroundings. As the gas collapses, it forms a rotating disk around the protostar, known as a protoplanetary disk. This disk is where planets, moons, and other celestial bodies begin to take shape. The pressure within the disk helps to clump together dust and gas, creating the building blocks of future worlds. Over time, these clumps grow larger, eventually forming planets that will orbit the newborn star. The pressures within protostars also play a crucial role in determining the star's ultimate fate. A protostar with enough mass will continue to collapse until nuclear fusion ignites, marking the birth of a main sequence star. However, if the protostar lacks sufficient mass, it may become a brown dwarf, a celestial object that never quite achieves the status of a true star. This delicate balance between pressure and mass is what makes the study of protostars so vital to our understanding of stellar evolution. As we explore the pressures within protostars, we gain a deeper appreciation for the forces that shape the universe. These cosmic nurseries are not just the birthplaces of stars, they are the cradles of entire solar systems where the seeds of planets, moons, and life itself are sown. Next, we'll delve into the pressures of the cosmic microwave background, the faint echo of the Big Bang that still permeates the universe today. Now, let's shift our gaze to the faintest whisper of the universe's earliest moments, the cosmic microwave background. This ancient afterglow, a relic of the Big Bang, carries with it the echoes of pressures that once shaped the cosmos. Imagine a time when the universe was a seething, dense soup of particles and energy, compressed into a space smaller than an atom. The pressures during this era were unimaginable, driving the rapid expansion of the universe and leaving behind a faint, uniform glow that we can still detect today. The cosmic microwave background, or CMB, is essentially the universe's baby picture, captured when it was just 380,000 years old. At this point, the universe had cooled enough for protons and electrons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. This light, stretched and cooled over billions of years, now reaches us as microwave radiation, filling the entire sky with a faint, almost imperceptible glow. But within this glow lies a treasure trove of information about the pressures that once dominated the cosmos. The CMB reveals tiny fluctuations in temperature, variations so small they're measured in millionths of a degree. These fluctuations are the fingerprints of pressure waves that rippled through the early universe, created by the intense gravitational forces of matter clumping together. These pressure waves, known as baryon acoustic oscillations, acted like cosmic sound waves, compressing and rarefying the primordial plasma. Over time, these ripples influenced the distribution of matter, seeding the formation of galaxies and galaxy clusters we see today. What's truly fascinating is how these ancient pressures continue to shape the universe. The patterns in the CMB provide a blueprint for the large-scale structure of the cosmos, mapping out the distribution of galaxies and dark matter. By studying these patterns, scientists can trace the evolution of the universe from its fiery birth to the vast, intricate web of galaxies we observe now. The CMB is not just a snapshot of the past, it's a window into the forces that have shaped everything we see. As we ponder the pressures encoded in the cosmic microwave background, we're reminded of the universe's incredible journey from a hot, dense state to the vast, expanding cosmos we inhabit today. This faint glow, a remnant of the Big Bang, connects us to the very origins of space and time. Next, we'll explore the pressures generated when white dwarfs collide, a cosmic event that can unleash some of the most powerful explosions in the universe. Now, let's turn our attention to one of the most explosive events in the cosmos, the collision of white dwarfs. These stellar remnants, the dense cores left behind after stars like our Sun exhaust their fuel, pack an incredible amount of mass into a sphere roughly the size of Earth. When two white dwarfs spiral toward each other, the pressures involved are nothing short of catastrophic, often culminating in a spectacular supernova explosion. White dwarfs are held together by a delicate balance of forces. Their immense gravity tries to crush them further, but a phenomenon called electron degeneracy pressure pushes back, preventing total collapse. However, when two white dwarfs collide, this balance is shattered. The gravitational forces between them grow exponentially as they draw closer, creating pressures so extreme that they can ignite runaway nuclear fusion. This sudden release of energy can trigger a Type 1, a supernova, one of the most powerful explosions in the universe. The pressures during such a collision are staggering. At the moment of impact, temperatures soar to billions of degrees, and the material is compressed to densities far beyond anything found in normal stars. This compression forces atomic nuclei to fuse together at an incredible rate, releasing energy on a scale that can outshine entire galaxies. The shock waves from these collisions ripple through space, scattering heavy elements like iron and nickel across the cosmos, which eventually become the building blocks for new stars and planets. What makes these events even more fascinating is their role in shaping the universe. The heavy elements forged in white dwarf collisions are essential for the formation of rocky planets like Earth and even life itself. Without these cataclysmic events, the universe would lack many of the elements necessary for complexity and diversity. It's a reminder that even destruction on a cosmic scale can lead to creation. As we reflect on the immense pressures of white dwarf collisions, we're reminded of the universe's dynamic and interconnected nature. These events, though violent, play a crucial role in the cosmic cycle of life and death. Next, we'll explore the pressures created by interstellar magnetic fields, invisible forces that shape the movement of gas and dust across the galaxy. Now, let's shift our gaze to the invisible forces that weave through the fabric of space. Interstellar magnetic fields. These magnetic fields, though unseen, play a crucial role in shaping the cosmos, influencing the movement of gas and dust across vast distances. Imagine them as cosmic threads, pulling and pushing matter in ways that determine the birth and evolution of stars and galaxies. Interstellar magnetic fields are generated by the motion of charged particles, such as electrons and ions, within the vast clouds of gas and dust that fill the space between stars. These fields may be invisible, but their effects are profound. They exert pressure on the surrounding material, guiding the flow of gas and dust into dense regions where gravity can take over, eventually leading to the formation of new stars. Without these magnetic fields, the process of star formation would be far less efficient, and the universe as we know it might look very different. The pressure created by these magnetic fields is subtle yet powerful. It acts as a counterbalance to other forces, such as gravity and thermal pressure, helping to stabilize the structure of molecular clouds. In some cases, magnetic fields can even prevent gas from collapsing too quickly, slowing down the formation of stars and allowing for the creation of more massive and complex systems. This delicate interplay of forces ensures that star formation is a gradual and controlled process, rather than a chaotic free-for-all. One of the most fascinating aspects of interstellar magnetic fields is their ability to shape the large-scale structure of galaxies. They can channel gas and dust into spiral arms, creating the stunning patterns we see in galaxies like the Milky Way. These fields also play a role in the formation of jets and outflows from young stars, as well as the acceleration of cosmic rays, which travel through space at nearly the speed of light. As we explore the pressures of interstellar magnetic fields, we gain a deeper appreciation for the unseen forces that govern the cosmos. These fields are a reminder that the universe is not just a collection of stars and planets, but a dynamic and interconnected system, shaped by forces both visible and invisible. Next, we'll venture into the pressures found in stellar nurseries, where the seeds of new stars are sown in the densest regions of space. Now, let's step into the cosmic cradles of the universe. Stellar nurseries. These are the bustling regions of space where new stars are born, forged from the collapse of massive gas clouds under immense pressure. Picture these nurseries as the universe's workshops, where raw materials like hydrogen and dust come together under the influence of gravity, magnetic fields, and thermal pressure to ignite the spark of new stars. In stellar nurseries, the pressure is a delicate balance of forces. Gravity pulls the gas and dust inward, compressing it into denser and denser clumps. As these clumps grow, the pressure inside them increases, heating the material until it reaches the critical point where nuclear fusion ignites. This is the moment a star is born, and it's all thanks to the extreme pressures at play. But gravity isn't the only force shaping these nurseries. Magnetic fields, as we've seen earlier, play a crucial role in guiding the flow of gas and dust, creating intricate structures within the clouds. Thermal pressure generated by the heat of the collapsing material also pushes back against gravity, preventing the gas from collapsing too quickly. This interplay of forces ensures that star formation is a gradual process, allowing for the creation of stars of varying sizes and complexities. One of the most iconic examples of a stellar nursery is the Orion Nebula, a glowing cloud of gas and dust located just over 1,300 light-years from Earth. Here, hundreds of young stars are in the process of forming, their light illuminating the surrounding gas and creating a breathtaking cosmic landscape. The pressures within the Orion Nebula are so intense that they trigger the birth of not just individual stars, but entire star clusters, each containing dozens or even hundreds of stars. The pressures in stellar nurseries also have a profound impact on the types of stars that form. In regions with higher pressure, massive stars are more likely to form, while lower pressure areas tend to produce smaller, cooler stars. This diversity is what makes stellar nurseries so fascinating. They are the birthplaces of the entire spectrum of stars, from tiny red dwarfs to colossal blue giants. As we explore these cosmic cradles, we gain a deeper understanding of how the universe creates the building blocks of galaxies. Stellar nurseries are not just places of immense pressure. They are the engines of creation, where the raw materials of the cosmos are transformed into the stars that light up the night sky. Next, we'll dive into the extreme pressures found in the thin atmospheres of neutron stars, where atoms are crushed into a dense layer under unimaginable forces. Now, let's shift our gaze to one of the most extreme environments in the universe, the thin atmospheres of neutron stars. These remnants of supernova explosions are not only incredibly dense, but also host atmospheres where the pressure is so intense that it defies imagination. Picture this: the atmosphere of a neutron star is only a few centimeters thick, yet it's packed with atoms crushed into a dense layer under forces billions of times stronger than anything on Earth. In this ultra-thin layer, the pressure is so extreme that atoms are flattened and squeezed into a state unlike anything we encounter in our everyday world. Normally, atoms have a structure with a nucleus surrounded by orbiting electrons. But in the atmosphere of a neutron star, the pressure is so overwhelming that electrons are forced closer to the nucleus, creating a dense, almost solid-like layer. This compression is so severe that it alters the very nature of matter, turning atoms into a bizarre, ultra-compressed state. What makes this even more fascinating is the role of gravity. Neutron stars have surface gravity about 100 billion times stronger than Earth's. This immense gravitational pull not only crushes atoms but also creates an environment where even light struggles to escape. The pressure in the atmosphere is so high that it affects how light behaves, bending and distorting it in ways that challenge our understanding of physics. The thin atmosphere of a neutron star is also a place of extremes when it comes to temperature. While the surface of a neutron star can be relatively cool compared to its core, the atmosphere itself can reach temperatures of millions of degrees. This heat, combined with the crushing pressure, creates a dynamic and chaotic environment where matter is constantly being reshaped and transformed. One of the most intriguing aspects of neutron star atmospheres is how they interact with the star's magnetic field. Neutron stars are known for their incredibly strong magnetic fields, which can be trillions of times more powerful than Earth's. These fields interact with the compressed atoms in the atmosphere, creating phenomena like X-ray emissions and powerful bursts of radiation. These interactions provide scientists with valuable clues about the nature of matter under such extreme conditions. As we explore the pressures within neutron star atmospheres, we're reminded of just how strange and diverse the universe can be. These environments push matter to its absolute limits, revealing behaviors and properties that challenge our understanding of physics. Next, we'll turn our attention to the pressures of cosmic expansion and how they shape the large-scale structure of the universe. Now let's zoom out from the intense pressures of neutron stars and explore a force that shapes the entire cosmos, the pressure of cosmic expansion. Unlike the crushing forces we've discussed so far, this pressure operates on a grand scale, influencing the very fabric of the universe. Cosmic expansion is the process by which the universe stretches and grows over time, a phenomenon first discovered by Edwin Hubble in the 1920s. But what does this have to do with pressure? Well, as space itself expands, it creates a kind of negative pressure that pushes galaxies apart. This isn't the kind of pressure that crushes or compresses, it's a force that stretches and disperses, acting like an invisible hand guiding the movement of galaxies. This pressure plays a crucial role in shaping the large-scale structure of the universe. Imagine the cosmos as a vast web, with galaxies clustered along its threads and nodes. Cosmic expansion determines how these clusters form and evolve. As space stretches, it pulls galaxies away from each other, but gravity fights back, pulling them together. The balance between these two forces, expansion and gravity, creates the intricate patterns we see in the universe today. One of the most fascinating effects of cosmic expansion is how it influences the distribution of galaxies. Over billions of years, this pressure has caused galaxies to spread out, creating vast voids where matter is sparse and dense clusters where galaxies gather. These voids and clusters form the cosmic web, a structure that spans the entire observable universe. But cosmic expansion doesn't just affect galaxies, it also impacts the light traveling through space. As the universe expands, it stretches the wavelengths of light, causing it to shift toward the red end of the spectrum. This phenomenon, known as redshift, is one of the key pieces of evidence for the expansion of the universe. What's even more intriguing is that cosmic expansion is accelerating, driven by a mysterious force called dark energy. This acceleration adds another layer of pressure, pushing galaxies apart faster and faster over time. Scientists are still working to understand the nature of dark energy and how it interacts with the pressure of cosmic expansion. As we reflect on the pressures shaping the universe, it's clear that cosmic expansion is one of the most fundamental forces at work. It not only determines the distribution of galaxies, but also influences the ultimate fate of the cosmos. Next, we'll dive into the theoretical pressures at the center of black holes, where gravity becomes infinite and the laws of physics as we know them break down. Now, let's venture into one of the most mind-bending concepts in the universe, the pressure at the center of black holes. At the heart of these cosmic monsters lies a point of infinite density and gravity known as the singularity. Here, the laws of physics as we know them break down, and the pressure becomes so extreme that it defies comprehension. A black hole's singularity is the ultimate endpoint of gravitational collapse. Imagine squeezing an entire star or even multiple stars into an infinitely small point. The pressure at this point is so intense that it warps spacetime itself, creating a region where time and space cease to behave in ways we can understand. Theoretical models suggest that at the singularity, gravity becomes infinite. This means that any matter or energy that crosses the event horizon, the point of no return, is crushed into this infinitely dense point. The pressure here is so overwhelming that it overcomes all other forces, including the nuclear forces that hold atoms together. What makes this even more fascinating is that we can't directly observe or measure what happens inside a black hole. Our current understanding of physics, including Einstein's theory of general relativity, fails to describe the conditions at the singularity. This is where quantum mechanics and gravity are expected to merge, but scientists are still working to develop a unified theory that can explain these extreme conditions. One of the most intriguing ideas about black hole singularities is that they might not be points at all. Some theories propose that singularities could form loops or rings, known as Kerr singularities, which rotate at incredible speeds. These rotating singularities could create even more complex and extreme pressures, further challenging our understanding of the universe. As we ponder the pressures at the center of black holes, it's clear that these cosmic phenomena push the boundaries of human knowledge. They remind us that the universe is full of mysteries waiting to be unraveled. Next, we'll explore the pressures within dark matter halos, the invisible structures that surround galaxies and shape their motion. Now, shifting our focus to the invisible yet powerful forces shaping the cosmos, let's delve into the pressures within dark matter halos. These mysterious structures envelop galaxies, acting as cosmic scaffolding that holds them together and dictates their movement. Despite being invisible, dark matter halos exert immense gravitational pressure, shaping the very fabric of the universe. Dark matter, which makes up about 85% of all matter in the universe, doesn't interact with light or ordinary matter in the way we're familiar with. Instead, its presence is felt through its gravitational influence. Dark matter halos are vast, spherical regions surrounding galaxies, where this elusive substance is densely concentrated. The pressure within these halos isn't like the crushing forces we've explored in neutron stars or black holes. Instead, it's a gravitational pressure that subtly but profoundly affects the motion of stars, gas, and even entire galaxies. One of the most fascinating aspects of dark matter halos is how they influence galaxy rotation. Without the gravitational pull of these halos, galaxies would fly apart. The pressure exerted by dark matter creates a stable framework, allowing galaxies to maintain their structure over billions of years. This gravitational pressure also plays a crucial role in the formation of galaxies, guiding the collapse of gas and dust into the spiral arms and disks we observe today. But the story doesn't end there. Dark matter halos also interact with each other, especially during galaxy collisions. When two galaxies merge, their dark matter halos create a complex dance of gravitational pressures, shaping the resulting galaxy and triggering bursts of star formation. These interactions are a testament to the invisible yet dominant role dark matter plays in the universe. What makes dark matter halos even more intriguing is that we still don't fully understand their composition or behavior. Scientists use simulations and observations of galaxy rotation curves to infer their presence, but the exact nature of dark matter remains one of the greatest mysteries in modern astrophysics. As we explore the pressures within dark matter halos, we're reminded that the universe is governed by forces we can't always see. These invisible structures are the silent architects of the cosmos, shaping galaxies and influencing their evolution in ways we're only beginning to comprehend. Next, we'll turn our attention to the pressures generated by interstellar shock waves, which compress gas and ignite the birth of new stars. Now, let's journey into the dynamic forces that ripple through the vastness of space, where interstellar shock waves carve their mark on the cosmos. These shock waves are powerful disturbances that travel through the interstellar medium, the gas and dust between stars, creating regions of intense pressure that can spark the birth of new stars. Interstellar shock waves are often the result of cataclysmic events, such as supernova explosions or the collision of massive stellar winds. When a star explodes, it sends a blast wave racing outward at incredible speeds, compressing the surrounding gas and dust. This sudden increase in pressure can trigger the collapse of molecular clouds, the birthplaces of stars. Imagine a cosmic domino effect where the shock wave pushes the gas together, increasing its density until gravity takes over and pulls it into a new star. But shock waves aren't just destructive, they're also creative forces. As they travel through space, they heat the gas they encounter, causing it to glow and creating stunning structures like supernova remnants. These remnants are often visible as glowing clouds, such as the famous Crab Nebula, which was formed by a supernova observed on Earth in the year 1054. The pressure from these shock waves doesn't just compress gas, it also enriches the interstellar medium with heavy elements forged in the hearts of dying stars, providing the raw materials for future generations of stars and planets. Another fascinating aspect of interstellar shock waves is their role in shaping the large-scale structure of galaxies. As shock waves propagate through the interstellar medium, they can create bubbles and filaments of gas, carving out intricate patterns that influence where and how stars form. These structures are like cosmic fingerprints, revealing the history of shock waves and their impact on the galaxy. What's truly remarkable is how these shock waves connect the life cycles of stars. A single supernova can trigger the formation of dozens of new stars, which may eventually explode and create shock waves of their own. This cycle of destruction and creation is a fundamental process in the universe, driving the evolution of galaxies and ensuring that the cosmos remains a dynamic and ever-changing place. As we explore the pressures generated by interstellar shock waves, we see how even the most violent events in space can lead to new beginnings. These waves are the cosmic architects of star formation, shaping the universe one shock at a time. Next, we'll uncover the immense pressures within neutron star atmospheres, where atoms are crushed into a dense layer under unimaginable conditions. Now, let's turn our attention to one of the most extreme and mind-bending phenomena in the universe, the magnetic fields of neutron stars. These cosmic powerhouses are not only incredibly dense, but also home to some of the strongest magnetic fields ever observed. In fact, the magnetic fields around neutron stars can be trillions of times more powerful than Earth's, creating pressures so intense they defy imagination. To put this into perspective, imagine a magnet so strong that it could rip apart atoms from thousands of kilometers away. That's the kind of force we're talking about. These magnetic fields are generated by the rapid rotation and extreme density of neutron stars, which compress matter into a state so dense that a single teaspoon would weigh billions of tons. As these stars spin, their magnetic fields become amplified, reaching strengths that can distort the very fabric of space around them. The pressures created by these magnetic fields are so extreme that they can influence the behavior of matter in ways we're only beginning to understand. For instance, the magnetic fields can accelerate particles to nearly the speed of light, creating powerful beams of radiation that we detect as pulsars. These beams sweep across the cosmos like cosmic lighthouses, and the energy they carry is a direct result of the immense pressures generated by the magnetic fields. But the effects don't stop there. The magnetic fields of neutron stars can also cause star quakes, sudden shifts in the star's crust that release enormous amounts of energy. These quakes are so powerful that they can alter the star's rotation and even emit bursts of gamma rays, some of the most energetic events in the universe. The pressures involved in these events are so intense that they can momentarily outshine entire galaxies. What's truly fascinating is how these magnetic fields connect neutron stars to the broader universe. They can interact with nearby stars, planets, and even other neutron stars, creating complex and dynamic systems. In some cases, the magnetic fields of two neutron stars can collide, producing gravitational waves and bursts of radiation that ripple across the cosmos. As we explore the pressures of neutron star magnetic fields, we're reminded of just how extreme and dynamic the universe can be. These fields are not just a curiosity, they're a fundamental part of how neutron stars shape their surroundings and influence the evolution of galaxies. Next, we'll venture into the speculative realm of the multiverse, where pressures might exist in forms we can scarcely imagine. Now, let's take a leap into the speculative and explore the pressures that might exist in other universes if the multiverse theory holds true. The idea of a multiverse suggests that our universe is just one of countless others, each with its own unique set of physical laws and conditions. In some of these universes, the pressures could be unimaginably different from what we experience here. Picture a universe where gravity is 100 times stronger than in ours. In such a place, the pressures at the core of stars or within black holes would be exponentially more intense, potentially creating matter in forms we've never seen. Or consider a universe where the fundamental forces are weaker, leading to lower pressures that allow for entirely different cosmic structures to form. These alternate realities could host phenomena that defy our current understanding of physics. One intriguing possibility is that some universes might have pressures so extreme that they prevent the formation of stars and galaxies altogether. In these environments, matter could be compressed into exotic states that don't exist in our universe, or it might be spread so thinly that it never clumps together to form larger structures. On the other hand, some universes might have pressures that are perfectly balanced to create life-sustaining conditions, perhaps even more favorable than our own. The multiverse theory also opens the door to universes where pressure isn't just a physical force but a fundamental aspect of reality itself. In some of these realms, pressure might be tied to dimensions we can't perceive, creating effects that are entirely alien to us. For instance, a universe with extra-spatial dimensions could have pressures that behave in ways we can't even begin to model with our current understanding of physics. While the multiverse remains a speculative concept, it challenges us to think beyond the boundaries of our own universe and consider the infinite possibilities that might exist. The pressures in these alternate realities could be the key to unlocking new insights into the nature of existence itself. As we wrap up our journey through the universe's most extreme pressures, we're left with a profound sense of wonder. From the crushing cores of neutron stars to the speculative realms of the multiverse, these forces shape the cosmos in ways that are both awe-inspiring and humbling. What other cosmic mysteries are waiting to be uncovered? Let us know your thoughts in the comments below, and don't forget to subscribe for more explorations into the wonders of space. Until next time, keep looking up as we bring our exploration of the universe's most extreme pressures to a close. It's clear just how vital these forces are in shaping the cosmos. From the unimaginable densities at the heart of neutron stars to the crushing gravity near black holes, these pressures are the architects of the universe's most dramatic phenomena. They forge stars, create elements, and even influence the very fabric of space-time. We've journeyed through the intense pressures of supernova, the delicate balance within white dwarfs, and the speculative realms of the multiverse. Each fact reveals a piece of the puzzle, showing how pressure isn't just a force, it's a storyteller narrating the history and future of the universe. But the story doesn't end here. The cosmos is filled with mysteries waiting to be unraveled. What other extreme conditions exist out there? What secrets do they hold about the origins of life, the nature of matter, or the fate of the universe itself? The answers lie in the stars, and the journey to uncover them is just beginning. If you've enjoyed this deep dive into the universe's most extreme pressures, don't forget to share your thoughts in the comments below. What fact surprised you the most? What cosmic mystery would you love to explore next? And if you're as fascinated by the wonders of space as we are, hit that subscribe button and ring the notification bell so you never miss an update. Until next time, keep your eyes on the skies and your curiosity alive. The universe is waiting to reveal its secrets.